So today we are talking about the well-known all-pair shortest path problem. It's a very well understood problem in computer science, and it has a beautiful, even if somewhat counterintuitive algorithm. So let's go dive right into it here. So in the all-pair shortest path problem, we are given a graph. It's a weighted graph. That means the edges have weights on them. Those weights are represented by a weight matrix W. Weights can be anything fractional, such as, or double, such as like 5 or 7.6, etc. And the problem is that we want to find the distance between every pair of nodes, and hence we call it the all-pair shortest path. Here's a quick example. We have nodes named from A through O, and the edges have weights on them. For example, the nodes A, B have an edge between them with a weight of 4. So we want to find the all pair shortest path. That means between every pair B and M, for example, H and K, for example, to find the shortest path between that. Now, of course, our basic intuition is that we're going to have to go through other nodes, and the edges with smaller nodes, smaller weights are going to be favored. We are essentially looking for a shortest path. However, it's not clear on how to make an algorithm out of this intuition. And we can establish a basic notation. The basic notation can be that the Dij represents the distance between nodes I and J. Dii can be set to 0 because that's the shortest path. That's the distance between I and I itself. That's 0. And other than those Dii's, we are essentially trying to find Dij's for all the values of I and J. One observation we can make is that we don't know a Dij even if J is a neighbor of I, because sometimes the shortest path may not be the direct edge. It might be more indirect. So we can look at our first recursive formulation. It's fairly intuitive, even if it doesn't work, but I think it's fairly intuitive. In this case, what we would say is that Dij is minimum over either Wij, if you want to take the direct edge, or minimum over some intermediate node K, so that you go from Di to K and plus Dk to J. So essentially you go from I to some intermediate node K, and then from K you go to J. Now, why does this not work? It's not easy to make this work because consider if you have Dij, then you think about Dik. But when you want to compute Dik, then you will look for minimum over x, some other x intermediate node, dkx to dxj. So that means you go from k to x and from x to j. However, x, one of the x values it can be is I itself. So you're trying to compute Dij in terms of Dik. For Dik, you again need Dij. So that's sort of your infinite loop there. So essentially it does not impose a good enough ordering in which we should compute these values. So even though it's intuitive, we think of intermediate, but it's not clear which ones will get computed first. Here's a slightly different recursive formulation. It's also fairly intuitive. In this case, we make this a slightly tighter. We say Dij is minimum over some neighbor of I. So first of all, either we're going to take the direct edge Wij, which is not written here, but again, that you could impose. Or if you don't take the direct edge between I and J, assuming one exists, then you would take the minimum over K, where K is some neighbor of I. So it's not a random intermediate node, but rather some neighbor. And then you would go directly. So that means Wi to K, plus from K, you would go to J. Why this also doesn't work is similar to the previous case, that again, Dij would depend upon Dkj, Dkj would then again depend upon Dij. So still there is no order. However, I want to point out that this formulation is better because it is less ambiguous. And in this case, we term ambiguous in a similar sense to how we might say that they're ambiguous context-free grammars. Essentially, the parse tree can have more than one parsing path. So again, that's a related concept. Look out for a separate video on that. But for the purpose of this particular video, we can say that this recursive formulation, the attempt number 2, also doesn't work. So what works? What does work is this famous algorithm by Floyd Warshall. It comes up with a notation that's slightly different. It's slightly counterintuitive. So let's make sure we understand it. We assume that the nodes are numbered 1 through n. However, in this case, what we would say is that dkij is defined as the length of the shortest path from I to j using the set of nodes 1 through k as possible intermediate nodes. Now, this does not say that you have to use k intermediate nodes or you have to use how many intermediate nodes you have to use. You could use one of them, none of them, two of them. But this is the only nodes that we are allowed to use as our intermediate nodes. So dkij is essentially imposes this ordering that we are only allowed to use that particular set. And the set is implicitly defined by the number k. The set really is 1 through k. So in this notation, we don't say d1kij, we just say k, but the k is representing essentially the set 1 through k. Now, you can think of the distance in this if you want to understand what does dkij really mean. Essentially, it means that there's a distance between I and j in a graph such that all the vertices other than I and j and the vertices above k have been removed. So you only keep I and j, you keep the set of vertices 1 through k, and then whatever is the shortest path, that's what this construct represents. So it's fairly counterintuitive why this way, but it does work. And in this case, what we are really interested in is the nij, because of course, no constraint is presented to us. We just made this artificial constraint for the purpose of ordering. But eventually, we're not interested in any constraints, so we want to look dnij. Dnij would say the shortest path from I to j using the set of nodes 1 through n as possible intermediate nodes. And of course, 1 through n is the entire set anyway. So that basically means that you can use any node that you want as an intermediate node, which is the standard definition of the shortest path. And now in this case, we can say d0ij means that you're not allowed to use any node here as an intermediate node. So it's either wij. If wij is not defined, that is interpreted to be infinite. So that means if two nodes don't have an edge between them, essentially it's infinite. So that's basically is a Floyd Warshall notation. And I'll tie it back to the principle of optimality here. Now, Bellman's principle of optimality from 1957 book says that the optimal policy has a property where you have the initial state, the initial decision, then your remaining decisions should constitute the optimal policy from the state resulting from the first decision. Essentially, you are here, you take the first decision, you go till that point, and then you continue to follow the optimal decisions, optimal policy beyond that point. Now, many times textbooks, including the course textbook behind me, it also uses the term optimal substructure as an almost interchangeable, but I would point out that the Bellman's principle, as originally stated, is slightly more general because it talks about policies and sequence of decisions rather than just a data structure or decomposition of a static solution into parts. But still, it's a fairly related concept. That's the principle of optimality. Now, why does the Floyd Warshall formulation really work? Basically, the first two formulations that we tried, they are intuitive, but they are structurally unhelpful. So what that means is that we do not know what the sequencing is. But in this case, in the Floyd Warshall algorithm, it uses the concept of a set of nodes, which you can grow one by one. And therefore, you're able to use the recursive formulation. You're able to build the solution one step at a time. Now, one way to say this thing is that Bellman's principle, but then Floyd Warshall's state space or the sequence. Going back to the recurrence relation itself, we would say dkij in the Floyd Warshall algorithm, we would say dkij is either, again, that's the shortest path between I and j, using the set of nodes 1 through k as a possible intermediate nodes. In that case, it would either use the node k or not. If it doesn't use the node k, then we would simply say that dkij is equal to dk minus 1ij. If you're not going to use k, then don't use it. Then just go to k minus 1. Or if you are going to use it, that means you're going to go from I to K, using the K minus 1 as the possible intermediate nodes, and then again from K to J, using the same K minus 1 as the possible intermediate nodes. That's a recurrence relation. And the algorithm then is essentially very easily defined as follows, that you would say you would go from, you would start by D0ij, that's your initialization, and recursive step, you would simply say, it's dk I minus 1, dk ij is equal to minimum of dk minus 1 ij, or dk minus 1 ik plus kj. And there's a fairly straightforward algorithm. We can see from this particular recursive formulation, there are 3 nested loops here. So it's a very straightforward order and cube algorithm. The algorithm is super clean to implement. In the sense D0 is initialized very easily. dk only depends upon dk minus 1. If you see here, dk only depends upon dk minus 1. So therefore, you don't really need to keep all the previous dk values. In fact, you can only use 1 if you're careful, but it still, if you notice, you can just use 2, only keep the last one. That's all you need. And that's the beautiful, even if counterintuitive algorithm, Floyd Warshall algorithm for the well-known all-pair shortest path algorithm. And like I mentioned, it's slightly counterintuitive. The slightly more intuitive versions don't lead to a necessary ordering, but that's a beautiful algorithm.